I'm Yoshihiko Suzuki from Kyoto University, Japan. The title of my presentation is Control of Oscillatory Temperature Field in a Building via Damping Assignment to Nonlinear Koopman Mode. This is a recent work with my two graduate students, Mr. Kohei et al. And Mr. Naoto Hiramatsu. In this presentation, I'd like to talk about our recent activity of the utilization of Koopman operator framework to nonlinear control problems. Here is the outline of my presentation. First of all, I'd like to talk about measurement data motivating this work, purpose, and the contents of this presentation. In this presentation, we'll focus on control of thermal dynamics inside the room space. The upper figure here is a picture of research office in a group, Osaka Prefecture University, Japan. We made a measurement of temperature inside the rooms using environmental sensors. The lower figure shows the location of totally 28 environmental sensors. Our focus is here on into a unit with so-called variable air volume VAV. This room has totally the 4 indoor units. This VAV is a switching mechanism of the change of airflow rate from a unit to regulate temperature. This is typical of nonlinear elements in control systems. Here let me show measurement data on temperature in this room like this. The totally 28 curves show time series of temperature measured by the environmental sensors. The set point of temperature is 27 degrees of Celsius for the cooling operation in summer Japan. In this figure, you can see the temperature oscillates in time with a period of about 15 minutes. This is mainly due to the above nonlinearities of the control system and is the main target to be controlled in this presentation. Okay, the purpose of this work is to control the oscillatory temperature field in the room. Technical benefits of this control include the enhancement of energy efficiency and enhancement of comfort for the people inside the room. The main challenge here is how we regulate the nonlinear spatial temporal dynamics described by the typical nonlinear partial differential equation. Our solution is to the control problem is to apply the Koopman operator theory to this control problem. I'll briefly introduce Koopman operator theory after this introduction. One important advantage here is that this theory can manage the nonlinear dynamics in a fully data-driven manner. In this presentation, we derived a model-free controller for regulation of the oscillatory temperature field. I mean no need of dealing with nonlinear PTE. This controller is also regarded as a generalization of the conventional damping assignment to linear time invariant systems. Okay, let us move to the theory part of this presentation: Koopman operator, nonlinear Koopman mode, and the damping assignment to Koopman mode. Okay, here is a brief introduction to the Koopman operator and the Koopman generator for nonlinear systems. Now we consider the following nonlinear dynamical systems. X dot is equal to capital F of X. Small x is a state, the X dot is a time derivative of state X, and capital F is a nonlinear vector field. From unique solution of this ODE, it is possible to define the so-called flow as a nonlinear map from the state space capital X to itself. Then we can define the Koopman operator. For this, we introduce the space of observable, which is the space of the function defined on the state space capital X. The Koopman operator then capital UT acts on the observable F to generate new observable like this. In this is defined as the composition of F with flow ST. An important point is that this flow originally nonlinear and finite dimensions, while this Koopman operator UT is linear but infinite dimension. From this utils, we also define the so-called Koopman generator as the time derivative of the Koopman operators. This generator is also linear and infinite dimension. The so-called Koopman operator framework is that we exploit property of G's linear operator for analysis and control of the original nonlinear system. Okay, so let us introduce a key idea for the utilization of this Koopman generator for our control problem. Now we consider the following nonlinear control system with the input U. In this system, capital F is called the drift vector field that is again nonlinear. The Koopman generator for F is denoted by capital L, that is again linear. From these linearities, we can define the notion of eigenvalue and eigenfunction for the Koopman generator to drift. In this, the phi lambda is eigenfunction of the generator L associated with eigenvalue lambda. Now we introduce so-called mode variable G lambda by using the Koopman eigenfunction phi lambda. We often call this variable is Koopman mode. The eigenfunction phi lambda is a complex valued function defined on the state space. So the G lambda is a mode variable is again the generally complex valued. By direct calculation, the time derivative of the mode variables is derived as follows. An important point is that when no input, I mean U is equal to 0, and then the dynamics of the mode variable G lambda dot is simply represented by the simple harmonic oscillator. The above values of the absolute value of G lambda is the mode variable determines the magnitude of the associated mode oscillation for the nonlinear systems. These absolute values become the target for the regulation of the mode oscillation. Okay, here is the main idea in this presentation. The idea is based on the simple harmonic oscillator and to determine the input to U such that the magnitude of the target mode is damped in time. To formulate this idea concretely, we introduce so-called polar representations of the mode variable G lambda. In this, the variable R describes the absolute value of the mode variables, and its time derivative, I mean R dot, is presented here. Again, you can see that when no input, I mean U is equal to 0, and then R dot is equal to 0. This implies no damping for the associated mode oscillation without any control. To assign the damping effect to this mode by control, we synthesize the dynamics of Earth as follows. Here, the capital D is a positive control parameter determining the degree of damping. In this equation, the eigenfunction phi lambda and the argument theta are functions of the state, original state x. So this synthesis implies that the input U is determined in like state feedback form. This is our controllers for the damping assignment to Koopman mode. As we show below, this controller can be synthesized from data only, no need of the underlying nonlinear systems. In this sense, this controller is a model-free. Also, from this formulation of simple harmonic oscillators, this idea is regarded as a generalization of the damping assignment to linear time invariant systems. Okay, from here we apply the damping assignment controller to the regulation of a temperature field. Okay, here is a modeling for control synthesis. The above figure shows the physics-oriented representation of the target systems. The controlled plant is the target room space with a lambda disturbance of outdoor temperatures. The dynamics here are described by a typical partial differential equation. Okay. The output of this plant is the indoor temperatures. Also, you can see the air conditioning system with VAB that causes oscillatory response to the output. The total system is represented by the nonlinear partial differential equation. For our control purpose, we consider the following model for oscillatory response as a nonlinear ODE. For this, the nonlinear vector field, capital F, represents the oscillating response of the indoor temperature. Then it is possible for us to introduce the Koopman generator L for the controlled load system. The output of this model is again the indoor temperatures sampled at 4 locations via sensors. The input U here is used for the damping assignment control proposed in this presentation like this. In the next slide, we show the damping assignment controllers added in this system. Here is the damping assignment controller for our application. A crucial point of this control is how to estimate the Koopman eigenfunction phi lambda directly from data. There is a very famous algorithm so-called extended dynamic mode decomposition EDMD. In this, the eigenfunction is approximated as a linear sum of the basis function like this. The basis function gamma x, that is a vector valued function, are designed by users, and the coefficient here is estimated from data. In our application, we consider the two sets of basis functions, linear and nonlinear sets. The question comes up here is how the choice of basis function affects the control performance. Okay, this slide shows the control simulations. The upper figure simulation without damping assignment control, and the lower figure as a simulation with control. The time series are the temperature at the 4 locations in this map. All these simulations were performed with a nonlinear partial differential equation. In the upper figure, you can see the sustained oscillation of the temperature without control. In the lower, the left, the figure is for the control simulation based on the linear approximation of Koopman eigenfunction. On the other hand, right is based on the nonlinear approximation. From these figures, clearly you can see the nonlinear approximation Koopman eigenfunction provides the better control of the damping assignment. This oscillation is clearly damped in time. This shows the effectiveness of the proposed damping assignment to the control of oscillatory temperature field. Okay, finally, let me conclude this presentation. In this presentation, we consider the control of oscillatory temperature field inside the loop. Based on so-called Koopman operator theories, we derived the simple model-free controllers for regulation of oscillatory temperature field. That is the damping assignment to a nonlinear Koopman mode. In this presentation, we have two main messages. One is this controller is nonlinear generalization of the conventional damping assignment in the linear harmonic oscillators. Second one, the control is effective for the regulation of oscillatory temperature field described by the typical nonlinear partial differential equation. In future work, we'll investigate this controller in practical 3-dimensional situations. Okay, that's all I have. Thank you for your kind attention.